Right. So we've had a little play with this simulation here, and we've said that the distance between these pair of lasers and the screen we've labeled as D. The distance between the two lasers is S. Now, normally this is going to be, rather than two lasers, it's going to be two slits, and then the light source would come, or the laser would come from behind that. So it would actually be one laser or one light source, and then that would split into two by using the double slits. But here we've just got two lasers. Um, and then the W is was the distance between any two fringes. It's not on this diagram because we changed it and messed around with it. Same with the S. And so down here we can see what we should have actually done. Um, so and this W is dependent on three things. It's dependent on the distance between the screen and the sources. You can see here the W is getting further and further apart as you go through, as you get further away. It's also dependent on the distance between the two slits, or in this case, the distance between the two lasers. And we noticed that actually, if you were to double the distance between the two lasers, then you'd half the distance between the fringes. So W is inversely proportional to S. And also we noticed that if you double the wavelength, then you double W, and so the distance between the fringes is directly proportional to the wavelength. So altogether, this comes out as this formula here. W is equal to the wavelength multiplied by the distance between the source and the screen, and divided by the distance between the two slits, or lasers in this case. By the way, this equation we have only put together by experimenting. What we're next going to try to do is prove it by using concepts, using our understanding of what's actually happening. So that's the next thing that we're going to do. We've understood it by experimental observation. Now we're going to try to understand it from what's actually happening. Okay.